Hello everyone. In this video, I would like to introduce you to a tool called OOMstaller. As the name suggests, it's designed to tackle a very specific, yet very painful problem that many of us who build large software projects face: swap thrashing. Our goal is simple: to help you build your projects faster by intelligently managing system memory at the most critical moments. So, let's set the scene. We live in an era of powerful, multi-core computers. To take advantage of this power, especially during long compilation tasks, we use tools like Make or Ninja with the -J flag, telling them to run as many jobs in parallel as possible. And for a while, everything is great. But then, as the build progresses, certain files, often large C++ template instantiations or linking steps, require a massive amount of memory. This is where the trouble begins. When the active processes demand more memory than is physically available, the operating system starts to rely heavily on what's called virtual memory. It begins frantically swapping memory pages between our fast RAM and our much slower disk storage. This state is known as thrashing. The system's disk light stays permanently on, responsiveness grinds to a halt, and the CPU ends up spending far more time managing memory than actually compiling your code. In the worst-case scenario, the Linux kernel invokes the out-of-memory killer, or OOM killer. This isn't a bug, it's a self-preservation mechanism to prevent a complete system freeze. The OOM killer identifies a process to terminate, usually the one consuming the most memory, to free up resources. While this saves the system, it crashes your build, making the entire situation incredibly frustrating and unproductive. This is precisely the problem OOMstaller is designed to solve. Instead of letting your system spiral into a state of thrashing or having the OOM killer abruptly terminate your build, OOMstaller proactively monitors the memory usage of your build processes. When it detects that memory is becoming dangerously scarce, it doesn't kill anything. Instead, it intelligently suspends some of the build processes. This allows you to run your builds using all your available CPU cores without the constant fear of hitting a memory wall. The key benefits are clear: you get to maximize your CPU usage for faster builds, you significantly shorten the total build time by avoiding the massive performance penalty of swapping, and you maintain a stable system throughout the entire process. So, how does this smart suspension work? The core idea is to be preemptive. When a process is suspended via a SIG-stop signal, its execution is completely halted. Its memory pages, even if they get swapped out to disk, will not be needed again until the process is explicitly resumed with a SIGCONT signal. This simple action has a profound effect. It ensures that the remaining, running processes have enough physical RAM to continue their work without triggering page faults. The performance gain from avoiding constant, high-latency disk I/O far outweighs the temporary disadvantage of not using a few CPU cores. We're trading a small amount of parallel processing for a huge gain in overall system efficiency, effectively preventing the thrashing death spiral before it even begins. Of course, we need to be smart about which processes we suspend. OOMstaller uses a clear and effective prioritization strategy. First and foremost, the process currently consuming the largest amount of memory is given top priority and will never be suspended. The logic here is this: the memory usage of this process is unlikely to decrease in the future. However, at some point, this process must be executed to the end. If we run another process first, it is possible that its memory usage will increase, and in some cases it may use even more memory. This would increase the total amount of swapping out, which would increase the total disk access time. For all other processes, the decision is based on their start time. Processes that started earlier are given higher priority to continue running. This policy is crucial because it prevents a situation where the same process gets repeatedly suspended and resumed, which could disrupt the build order logic that tools like Make and Ninja rely on. And importantly, OOMstaller is safe. It only ever monitors and controls the descendant processes of the command it was invoked with. This means your web browser, your text editor, and other unrelated applications will never be affected. Getting started with OOMstaller is incredibly straightforward. The build process is a standard make command. You just need to clone the repository from GitHub, cd into the directory, and run make. To use it, you simply prep and OOMstaller to your regular build command. For example, instead of make-J16, you would run OOM-Staller make-J16. A common and recommended practice is to use nproc to automatically specify the number of available CPU cores. So, a typical command would look like OOM-Staller make-J nprop. It works just as well with other build systems like Ninja, which is increasingly popular for its speed. For a Ninja project, the command would be OOM-Staller Ninja-J nprop. OOM-Staller is designed to work well out of the box, but it offers a few options for fine-tuning. One of the most interesting is max parallel thrash. By default, when thrashing is detected, OOM-Staller allows only one build process to run. However, if you have a very fast NVMe SSD for your swap space, the penalty for swapping is lower. In such cases, you might be able to reduce build times further by allowing a few processes to run in parallel even during high memory pressure. You can experiment with a setting like max parallel thrash too. A couple of important tips: if you ever need to stop OOM-Staller mid-build, please use Sigint by pressing Ctrl-C or Sigterm. Do not use Sigkill, as this will not give OOM-Staller a chance to resume the processes it has suspended, leaving them in a stopped state. If this ever happens by accident, you can recover by running the command killall-scon-u$, which sends a continue signal to all of your stopped processes. To wrap up, OOM-Staller provides a practical and effective solution to the memory wall problem in large-scale software builds on modern, multi-core systems. It directly addresses the issue of swap thrashing, which can cripple system performance. It does this not by killing processes, but through a strategic and intelligent suspension mechanism based on memory usage and process priority. The result is a tangible improvement in your development workflow, significantly shorter build times, the ability to fully utilize your CPU resources without fear, and a more stable system overall. Thanks for listening.